Lesson 95, we're taking a look at factoring higher ordered polynomials. So no longer just a linear, quadratic, or even a cubic, so to speak, but instead we're looking at polynomials with degrees like 5 or 8 or 10. It can be any number you want to. Not too often they'll go above 10 for you, at least in Algebra 2, but here we're looking at a polynomial with degree of 6. So for the first example, we just want to determine if 6 is a root of that given polynomial. Method number 1, take 6, plug it in for x, and see if we get a 0 for a result. That's a perfectly fine method. There's nothing wrong with it. The only thing with that method is, 6 to the 6th power is going to get you a really big number. 6 to the 5th and so forth will get you another really big number as well. So maybe instead of dealing with such big numbers and all that arithmetic, maybe we could just stick with some simple addition and multiplication. So I'm thinking from the method I want to go with is just synthetic division. That's the nice thing about synthetic division is it does not matter how big your polynomial is, it'll work for any given size. So we look at our coefficients that they give us. They give us a 2, they give us a negative 43, the next one is 75, 1,765, 857. Let's make sure we get the right sign, so that is a negative there. Negative 22,542. And last but not least, negative 30,240. Very good. Again, x is equal to 6, so it's not going to be negative 6, but just rather than 6, because, again, if it was the factored form, then we'd do the opposite, but because it's just x equals 6, that's what we're going to use. So very quickly, or if you want to at this point, you can pause the video, go ahead and do your addition and your multiplication. Once you're done, you can go ahead and replay the video or start it up again and see if you came up with the same answer. 2, 12, negative 31. And hopefully you got to the end where you got 41,040. So, long story short, this is what we're looking at, is that remainder. And if the remainder is something other than 0, then it is simply not a root. If it would have been 0, then we would have been able to say, yep, 6 is a solution or 6 is a root to the polynomial. Last example. Notice for this one, they're not asking us to determine whether a particular value is a root, but instead, we just simply want to find all the roots. Now, if we take a look at this polynomial, x to the 5th, so we have a degree of 5. There are no methods that we've covered up to this point that'll help us solve this thing. I guess one thing we could do is that we could go into Desmos or a graphing calculator. We could graph this polynomial and see where our x-intercepts would happen to be at. That would be one way we could find our roots. But as far as pencil and paper goes, we haven't covered it yet. So that's why I wanted to do it in this video. The method is called the rational root theorem. So yes, we're using the theorem as a method to go ahead and help us solve this thing. Now if we break it down, rational just means, okay, it could be a fraction or it could be an integer, it could be a whole number, any of one of those things. The roots, obviously, those are our solutions, those are our x-intercepts, and this is a theorem, so this is an idea that has been proven to be true. It works for any given size polynomial. So here's how it goes about. I think once we get through the first example, it'll make a little bit more sense. We want to start by looking at the P over Q. Now, what in the heck is P over Q? Well, the P value is your constant term. So our constant term here is that 6 value. So let's go ahead and make that P value the 6. And then our Q value is our leading coefficient. Now, it's not there, so it's understood to be a 1. So this is again the beginning of the rational root theorem. We take our p over q, our constant term over our leading coefficient. Now we want to look at all the factors of each one of those. So the factors of 6 that come to mind. Well, the trivial case is 1 and 6. The next one would be 2 and 3. And that's it for the factors of 6. Factors of 1, that's really nice. The only factor of 1 is itself, so that's all we have to worry about. So we're about there. Now what we need to do is we need to take the combination of the numerators over all of the denominators. Once again, the good news is there's only one denominator. So only one possible combination there. 1 over 1 will get us 1. 2 over 1 will get us 2. 3 over 1 will get us 3. 6 over 1 will get us 6. And last but not least, for all of these, just do a plus or minus for each one of those. Now, I'm going to kind of talk about something a little bit different. It isn't associated with this problem, but suppose we had a denominator of 2. Suppose the q value was 2. So the factors would be 1 and 2. Now we would have to put all of our numerators over 2 to come up with those combinations. 1 over 2 would mean that we would get plus or minus a half. 2 over 2 would happen to be 1, which we already have up in that list, so we don't necessarily need to rewrite that. But then we have 3 over 2 would be a combination, and then 6 over 2 is 3. We already have that up there in our list, so we wouldn't have to rewrite that. But you get the gist. It's every numerator over every denominator, every possible combination you can have. Now, what did we do? We came up with 4 numbers, the positive value of those 4 numbers along with the negative value of those 4 numbers. So really what we've done is we've created a list of 8 values. And those 8 values are the list of possible roots that it could be. So what the rational root theorem has done at this point is it's taken all of the numbers on the number line, infinitely many numbers, infinitely many roots, and it has narrowed it down to these possible 8 roots. So it's done a lot of the work for us. The problem is it has not found the exact roots for us. And that's what we need to do. So now what we need to do is kind of a trial and check to see which one of these 8s are the exact roots. How do we go about doing it? Well, synthetic division has always been good to us, so I think that's the method we want to use. So the highest one is x to the 5th, so that's a 1. 4x to the 4th. Now notice we don't have an x to the 3rd, so I need to plug in a 0 there. Make sure you make note of that. -10, -1, and 6. And again, it's a guess and check is what it is. Now my advice is if they give you 1 as a factor, start with that. So 1 or -1. Let's start with +1. And let's see what happens. We'll drop the 1. Multiply to get 1, add to get 5, multiply to get 5, add to get 5, 5, -5, -5, -6. And sure enough, on the very first guess of 1, we found our very first root. And we can go ahead and make that list over here. So our roots, first one was +1. Now, this is the nice thing about synthetic division is that each time you find a root, it's going to start breaking that polynomial down a little bit more each time for you. Okay, so instead of looking at the 1, the 4, the 0, the -10, the -1, and the 6, we're actually going to look at these bottom numbers. The 1, the 5, the -5, and the -6. Notice that's one less number that we have to worry about. So now what we want to do is, again, guess and check. You could move on to -1 if you wanted to. You could try 1 again. There's nothing saying that 1 doesn't appear more than one time. It could have a multiplicity of 2 or 3. But let's go ahead and try -1 now. So -1. Drop the 1, -1, 4, -4, 1. And we'll keep going. Multiply those two, we get 6. And wouldn't you know it, we just found our second root. Because the remainder is 0, -1 now is a root for us. And again, we broke it down even further. So now let's go ahead and try another number. Let's try 2. So 2, 1, 4, 1, -6. Drop the 1, 2, 6, 12, 13. And once you know it, that's not going to work for us, okay? Because we're going to get a remainder something other than 0. So we can actually cross +2 off our list. We'll know in the back of our mind, hey, never try 2 again because it's not going to work for us. Let's go ahead and try -2. Drop the 1, -2, 2, -4, -3, 6, and voila. So it appears that -2 is going to be a root for us. And here's the nice, once again, notice our final numbers are 1, 2, and -3. Now, what it's done is it's broken that polynomial down even further and further for us each time. This is our remainder, this is our constant term, this is our x, and this is our x squared. If we had another number, it'd be x cubed. If we had another number, it'd be x to the 4th. But what we have here now is we actually have the quadratic x squared plus 2x minus 3. So instead of doing synthetic division, if you get down to those last 3 numbers, you could see if this thing would factor for you. You could go back to, okay, it's a quadratic, now we're going to try and factor this thing. So I'm actually going to do that. 1 and 3. We'll make that 3 positive, this one negative. So sure enough, there's a 1 and there's a -3. Now the 1 we already had as a root, so I don't need to write that down. If we wanted to, I guess we could make note that, hey, this one has a multiplicity of 2. But our last remaining root that we found was -3. And there are all the roots. Now, the last thing that I wanted to note is let's go back to the list of possible roots that we came up with. The first one was +1. Another one was -1. Another one was -2. And the last one was -3. So again, this kind of ties this thing all together. The rational root theorem again gave us a list of all possible roots that could come from this thing. It did not give us the exact ones, but notice it didn't lie to us. All the roots that we found just so happened to be in that list. We just had to dig a little deeper to find out which exact ones they are. So for your homework today, you're going to be doing the rational root theorem for all these. Take your time, put P over Q, and again, it's going to be a lot of trial and error. You're going to get really, really good at that synthetic division.